Hi everyone, I'm Dr. Surjit Singh. Today we'll discuss the Leetcode problem, longest increasing path in a matrix. This will explain the use of a DAG. Let us begin. We are given a two-dimensional array in which all the cells are 0 or positive. We are to find the length of the largest path in which adjacent cells are in increasing order. In the first method, we will use the simple form of DFS. M, N, and dir are instance variables of class. Matrix is a two-dimensional array. The cells of the matrix will become the vertices of the graph. Each vertex has four edges that are its neighbors in four directions. If the matrix is empty, the answer is 0. M and N are the number of rows and columns in the matrix. There is a list of four increments in x and y to get neighboring cells in four directions. We set ans equal to 0 and start loops to scan all the elements in matrix. First starting element is 9 at 0, 0. We start DFS to find paths starting with 9. 9 is present at 0, 0, so 0, 0 is copied to XY in DFS. We initialize ans to 0. We start a loop that runs 4 times to cover the 4 directions of the adjacent cells of 9. In the first iteration, dx, dy are 0, 1 to get new positions xx, yy, where 3 is present. We ensure that the cell xxyy is not outside the matrix and that it is greater than the original number. As 3 is not greater than 9, the result is false. We go to the next iteration to change direction. New values of dx, dy are 1, 0, so xxyy becomes 1, 0, where 6 is present. Even 6 is not greater than 9. Other two directions of 9 are outside the matrix, so if statement is skipped in all the four cases and we come out of the for loop and we return 1 to the main function. 1 is more than the previous value of ans, so its new value becomes 1. This indicates that the path originating from 9 is of only 1 unit length. New values of xy are 0, 1, which starts new DFS. We process neighbors of 3. Its first neighbor is 4, which is greater than 3, so next DFS starts. Its right neighbor is not present, while its down neighbor is 8, which is more than 4, and another DFS starts. All the four neighbors of 8 are either not present or less than 8, so the for loop terminates and it returns 1 to the previous call, where ans becomes 1. 3 is less than 4, while other two neighbors of 4 are not present, so it returns 2 and ans becomes 2. Down neighbor of 3 is 6, which also starts a DFS. Its right neighbor is 8, which starts another DFS. No neighbor of 8 is more than it, so this returns 1. No other neighbor of 6 is more than it, so it returns 2 to the previous call. Old value of ans is already 2, so there is no change. The left neighbor of 3 is 9. A DFS will start for this also, but this will return 1 as the ans, so the max value of ans remains 2. Processing of 3 is over and it returns 2 plus 1 to the main function, which is more than the previous value, which is 1. So ans there becomes 3. This means that starting with 3, the longest increasing path is of length 3, be it 348 or 368. The process will continue for all the cells of the matrix. We will come across the path 1269 originating from 1, which has length 4, and this final value of ans is returned as the result. In the worst case, there can be 2 to power m plus n calls, and this becomes the time complexity of this method. Unfortunately, this method exceeds the prescribed time limit. There are mn cells in all. In worst case, this can be the size of the call stack. In this method, memoization is added to DFS. there's no need to find the longest path originating from a cell over and over. So we save them in a matrix. We initialize an m cross n array named memo to all zeros, which is accessible to all the functions. This will be used to save DFS results. We start xy loop as before and call DFS. We use memo xy to save ans of DFS. Memo xy is 0, so we proceed further. Its neighbor 3 and 6 are both less than 9, so we come out of the for loop and increase memo 00 to 1. Ans becomes 1 in the main function. In the next iteration, memo 01 is also 0. Its right cell starts a new DFS call, whose lower cell starts yet another DFS call. Memo 12 is increased by 1 and is returned to the previous call where it is stored in memo 02. At this point, we have processed all the neighbors of 4 that are more than it, and memo 02 is increased to 2. This value means that 48 is the longest path starting from 4, whose length 2 is returned and is stored at memo 01. Down cell of 3 starts another call of DFS function. Only neighbor of 6 that is more than it is 8, for which memo is already determined to be 1. So 1 is returned without processing 8 and is stored at memo 11. All neighbors of 6 that are more than it have been processed, so memo 11 is increased to 2 and returned. Third neighbor of 3 is 9. We already know that memo of 9 is 1, so we do not have to reevaluate it. As it is less than 2, so it is ignored. All neighbors of 3 have been processed and we come out of the for loop. Memo 01 is increased to 3 and returned to the main function. This 3 means that both of the longest paths starting from 3 are of length 3. We have already found 5 out of 9 cells of memo, which we will use in future iterations. Process will continue in the same way. Each cell of memo is determined once only. The final result is the same. There are mn memo cells. Each cell is processed only once and has 4 neighbors. Their processing time complexity is 4mn, which is same as mn. Memo cells are mn, which becomes space complexity. Size of the call stack is much less than mn. In this method, we treat the problem as DAG. We start with the same matrix. First step is to surround the matrix with zeros on all the 4 sides to get a supermatrix. We fill first row of supermat with n plus 2 zeros. In a loop, we copy rows of the matrix padded with zeros on both the sides, followed by another row of zeros. We increase m and n by 2 each. We now proceed to find out degree of each node. We initialize it to all zeros. One by one, we check neighbors of all cells. All the neighbors of 9 are smaller than it, so out degree of 9 is 0. Let us show it in a DAG. 3 is less than 4, 6 and 9, so its out degree is 3. And DAG grows like this. 4 is less than 8, so its out degree is 1. Further, we get, and finally this. 9 and 8 are leaves for which out degrees are 0. We define a list named leaves to find them. We start a pair of loops to scan entries in out degree. Whenever out degree is 0, we append the tuple xy in leaves. Now we proceed to find height of DAG. We define height equal to 0. We start a loop to process the list and increase height by 1, and we start a list named new leaves. In the first iteration, we process cell 11 where 9 is present. We inspect its 4 neighbors. Peeling off of 9 means decreasing the degrees of its neighbors by 1 if they are less than it. So degrees of 3 and 6 are decreased by 1. Out degrees of some boundary cells may also change. Out degree of 6 has become 0, so we save its position in new leaves. Now we peel off 8 present at 2, 3. Out degrees of 1, 6 and 4 are decreased by 1. All the 3 have become 0, so they are added to new leaves. Processing of leaves is over. For next iteration, new leaves replaces leaves. Leaves is not empty, so height is increased by 1 and new leaves become empty. In this iteration, 1, 6, 4 and 6 are peeled off from DAG like onion leaves. And we get this. In next iteration, we peel off 3 and 2 to get this. In last iteration, 1 is peeled off and height becomes 4. In next iteration, leaves is empty. We come out of the loop and we return height as the final answer. Each vertex is processed once. They have 4 edges each, so Mn is the time complexity. Space used by a supermatrix and out degree are of the order of Mn. Thank you for your time. Please subscribe to my channel and like my videos.